Welcome everyone back for this keynote session. So I just welcome on behalf of organizing committee of International Conference on Intelligent Robotics and Automation and Mechatronic System, IRMAS 2021. So welcome Professor uh, Professor Leonard Thompson. So just to give a brief introduction about him. So he is currently Professor and Director in MEMS Research Center, Material Science and Manufacturing Division, Mechanical Engineering Department in Istanbul Technical University. To say about his qualification, he completed his BSc in Mechanical Engineering from Bohensee University and went on to complete his master's in material science engineering from Carnegie Mellon University, USA, and PhD from Penn State University, USA. So his research interests are about surface science, material handling, nanomaterials, nanotechnology, infant deposition, NEMS, microfluidics, biomaterials, plasma nitring, microsystem design, and many other related stuff. So his credentials goes on to pages, so I couldn't able to read out everything. So just to put short, he's a very active researcher and have a very much decades of experience in developing this MEMS and microfluidics. So we are very passionate here to have you, sir, to our conference, and I just request you to start your presentation. Thank you. Thank you.
Thank you very much for kind and nice introduction. I wish I was there, but unfortunately, because of this current, pandemic issues, hopefully next year, let's say. Let me share my screen to start with my, presentation. Do you see my screen now?
Yes, sir. Yes, sir.
Good. So, as you said, I'm going to give what we are doing, and first I'd like to introduce a little bit theoretical background on the inertial microfluidics in biological applications. But before going further, I would like to take this opportunity to introduce my university to the audiences over there. My university is going to be celebrating its 25th anniversary 2 years later. So it's an old and I think the oldest engineering school in Turkey from Ottoman time. So we are a purely engineering school and research university. We have 5 different campuses scattered all around the Istanbul, city of Istanbul. And we have over 2,000 academic staff, PhDs, people working on the research, over 40 degree programs and 144 graduate degree programs, and many of them are in English character. And moreover, it's just a short list of some of the research center established in our university, just for the sake of a brief introduction. And moreover, we have a very strong techno park embedded in the campus, with integrated with the university, that gives us really a good leverage on application of the research on industry. And I'm not going into the details of the all sorts of things, but you can take a look at it by yourself. And before going further, this is the just snapshots of ITU Nanotechnology Research and Application Center. Basically, it is centered around a clean room. This is some of the pictures from the clean room. More snapshots, as you see on the screen. And we have also another clean room, a little bit, a smaller one with respect to the ITU Nano. That one, we have it is more student-oriented. The previous one more profession-oriented, basically. And we have attached to the MEMS clean room, we have also very nice, well-equipped cell room, actually, to run experiments on the cells in our research. Okay, let's start with what I'm going to tell you today. First of all, I would like to introduce what is microfluidics. for those of you maybe not so much familiar about this topic, the microfluidics is a kind of, maybe you heard about that to some extent, but it's you can able to make a portable devices, portable characterization devices in not only in biological sciences, but also some other engineering fields as well, chemical, mechanical, all sorts of things. And in such systems, you are supposed to be, expect to use low reagent consumptions, compatible with the size of bioparticles. That's why it's important to be used in such biological applications. And also, because of the scaled character, you're going to get the improved sensitivity, and also it should be integrated to other technological components. And moreover, on top of the, what I have told you, it's modular, cheap, and it can be used one at a time. Specifically, since we are going through a pandemic issues, there are some microfluidic-based devices people offered in the last couple of months to detect or to diagnose COVID-19 virus in a very short, in a very effective way. That's another application of microfluidics in that field. And in the microfluidic field, we have basically what in my research area, what I am doing, I am trying to do particle manipulation by fluid dynamics, by the fluid characteristics. But there are two ways of approaching that. The first one is the passive method. The other one is the active methods. In the passive methods, you don't have any external field. You are using physics behind that, like geometry and physics. In the active methods, actually, you are imposing an external field on the particles. Like there are so many different types: electrophoresis, dielectrophoresis, magnetophoresis, acoustophoresis. Actually, we have also studied dielectrophoresis and acoustophoresis on our research, but I am not going to explain what we have done on this field in this today in this talk. Moreover, I'm going to deal with I'm going to spend more on time what we have done on one of the passive separation processes, as you're going to see in a moment. But before going into details, in the passive separation processes, there are different approaches as well, like hydrodynamic chromatography, pinch flow fractionation, sedimentation. Actually, this is such approaches is achieved by the design and how you apply the fluids onto the system. If you are cleverly designing the system, you are going to manipulate microparticles or bioparticles in the microchannels. Specifically, inertial microfluidics, one of the powerful methods in the passive microfluidics. Why it is so is the following. Actually, inertial microfluidics is nothing but just a search process in which the target is to be found by removing whole volume on it. It's just you are not looking at the target, but you are removing all the other things, all the other things on top of the target. It's just the reverse of it, actually. But it's not so much difficult as it is said in this sentence. And it is cheap and easy to apply, inertial microfluidics. And with respect to the active methods, inertial microfluidics can be operated at very high throughputs. It does have a very high controllability, and you can play with the inertial forces with different design of the microchannels. And also, up until now, it has been proved that it is one of the best methods to deal with the particles in the microchannels. Can be adaptable, can be also a part of the dynamics or active methods or other MEMS system as well. Just one slide how you can manufacture microfluidic devices very schematically. As you see, you're going to start with, in most of the cases, silicon wafer. You deposit photoresist material. It's a polymeric material, sensitive to the light. With the use of the appropriate light, in this case UV light, and then by means of the masking, some of the parts are open to the light and they are transparent, the other parts are opaque. Based on the which part's opaque, which part is transparent or open, you're gonna get certain pattern on the surface over here. It's just, you know, I mean, if you take a look at the real pictures, what we are doing is the following. You know, this is the you know, the wafer on the spinner, and at the end you may not see clearly, but there are some small figures over here. This is a PDMS polymeric material, and those small you know, the lines not so clearly visible. These are the microchannels that you can work with. Actually, if you a little bit concentrate on what is going on, what is the missing, what is the physics behind that? In the inertial microfluidics, there are two competing forces. The first one is the wall-induced force, which is related to the A to the 6. This is the A is the particle size, and another one is a shear gradient force, which is also proportional to the A to 3. These are important. When you combine those things, you come up with the lift force. The lift force is, you know, proportional to the 8 to the 6. You know, since that the force acting or force you are using to manipulate the particles in the microchannels is heavily dependent on the power of the size of the particle under test. So you can discriminate the particles with a very small dimensional difference. That makes this, you know, the approach very powerful in micro manipulation of the particles. Moreover, if the channel is curved, if there is a curvature of the channel, there is another force acting on the particles. We call that Dean force. Dean force related to only the A, but it's also a very strong force because it makes the particles circulating at the cross section of the, you know, the channel, so that it will the force acting as an inertial force, just explained one slide before, is going to be equilibrated with Ft, so that you will end up with equilibration of the particles in the channel. Okay, actually these are the basic physics behind what we are doing, why we are using that. You know, the parameters to be studied, the particle Reynolds number, fluids Reynolds number, threshold. There is a one number, that dimensions number, threshold number, and it to get the particle concentration or manipulation of the particle, lambda should be bigger than 0.07, and particle number should be bigger than 1, and required channel to achieve your target. That will be also, that must be calculated, so that you are going to define how long your channel it could be. These are there are some other secondary important parameters, but these are basic parameters that you should work to come up with a certain design. But it is not that much simple, and there are many alternatives by design. If you're going to use straight channel, you can use curved channel, only the curved, not straight. You're going to use spiral, you're going to use asymmetric spiral channel, or you're going to use expansion and contraction kind of channels, or combination of that. By combination of that, all the force acting on the particles are going to be behaving differently. By cleverly using them, each one of them, or combined forces acting on the particles, you come up with the particle manipulation on the microchannels. That is the engineering part of the, this phenomenon. You know, we have studied at the very early times, at the very beginning of our study, we have studied contraction and expansion type of inertial microfluidics. We have changed length, as you see over here, the width number 2, width number 1, and the alpha angle over here. By playing with those parameters, we have run so many experiments by different flow rates, as you see over here. And then we're gonna monitor that, the characteristic of the, you know, the flow particles. These are the green lines are nothing but just a train of the particles, microparticles. The dimension of the particle which is making the green lines is 9.9 micrometers in diameter, fully circular sphere character particle. You know, by playing with those, as you see, maybe at a certain angle and at a certain flow rate, the particles separated from each other. In some cases, they're behaving as a just a one line kind of things. This is nothing but just, if you're gonna really understand physics and correctly design the system, you come up with the successful manipulation of the particles in the microchannels. We have done many experiments, many experiments by changing, you know, each you know, the legend over here representing, you know, the one experiment, actually one design, different, and it is plotted by the particle Reynolds number, and this is the quality of the flow. And depending on in some cases we get single focus, in some cases we have two focus, double focus, lower focus, or upper focus kind of things. Or we can get only upper focus, or only lower focus kind of things. Okay, I mean, these are that systematic study of the experimental study of the fluidic behavior in the given design show you. You know what we have noticed, that there is a certain physics going on. If there is no alpha is 90 degrees, if alpha is getting lower and lower, we're going to get an effect of the wall. Effect of the wall force is going to be changed. In this case, the wall force is going to be 0, but it's getting bigger and bigger. That is creating double focus, single focus, so on and so forth. Okay, I mean, this is what we have seen over here, actually. And moreover, we have you know, done a different approach. We have utilized two different design, combine each one of them on top of each, come up with a very different design not studied before. You know, such a design, fully circular, studied before very clearly, and also asymmetrical curved channel also, but on a straight line, studied very deeply. What we have done, we have combined on top of each other. I mean, we have asymmetrical channel just transferred onto the curved channel, so that we get such a hybrid approach. We call it sunflower design. This is the design, you know, details of the final design of we have, and here is some dimensional effects, some dimensional spectrum of our design. You know, the design of the system we have studied. What we have seen, much better, superior performance of the particle manipulation. As you see over here, this is the inlet. Again, those green lines are nothing but just a continuum green particles, 9.9 diameter of the spherical particles, fluorescent particles. This is at the inlet. This is our sunflower. And we get, in the first turn, we get certain picture, second turn, another picture, third turn, an outlet. And at the bottom, this is our sunflower. At the bottom, only that circular, not a sunflower, just a circular. And as you see, there's a big difference in quality of the particle manipulation. I'm going to show some more pictures in the coming slides. Moreover, we have done in a very big range of, the flow rate, starting from 0.3 microliter per minute to the 1.5 microliter per minute. And we've seen that 9.9 micrometer fluorescent particles is giving us very nice focusing quality over a wide range of flow rates. As you see, in the focus line, in the defining of the focus line quality, you see that there is a very sharp, almost one line, all the particles back to each other is a kind of train line at the outlet in the sunflower geometry. And this is how we can normalize the focus. This is the sunflower, the focus response we have measured, and this is the focus quality from other designs. But by using such a focus quality, dimensionless focus quality number, we come up with the focus quality measurement, actually, or the definition merit. This is much better response of all three different designs. Please concentrate on this one. In this one, the top one is a sunflower. The triangles from the spiral one, the circular are from in a linear fashion, but in a non-symmetrical, the curvature. The spiral, the sunflower behaving much better over a wide range of, the flow rate. Similarly, you can see the same kind of approach, but in this case, there are two different particles. The one, let me get the pen. This is the green particles, which are under focus because it is satisfying the focus quality, as I have explained before. And at the background, as you see, maybe red particles, the diameter is much smaller, 3.3 micrometer. They are not under focus. So if you're going to use two different particles in the channel, the unfocused particles are going to deteriorate the quality of the focusing for the other particle, which is under focus. But even in this case, as you see over here, this is our sunflowers over a wide range of focus rate. Okay, this is the, and also we have run cell measurement, HeLa 60 cells measurement. Also, we have got very nice focusing quality for the living cells, HeLa 60, HL60 cell measurement. You see on the screen, this focus quality almost over 90% over a wide range of flow rate, and even for different design. The first design is the height is 50 micrometer, the height of the channel. The second one is the 60 micrometer. We have also studied two different cells, erythrotic cells and the HL60 on together. As you see over here, maybe the second figure is much better. This is in this area, okay, you have the red blood cells over here. It's a line of the red blood cell. In this area, this is the HL60 cells. Even though you have cells not under focus, which are affecting the focusing ones, but in that case, because of the design quality, HL60 cells are successful, focused or manipulated in a given design. Moreover, we also studied particle-particle interaction, and this is we have published a couple of papers on that. One of them is under under review now. The other one is already published. What we have seen that the degree of the curvature, as you see over here, degree of the curvature is going to be very critical parameter in changing the quality of the interaction. I'm not going to going into details, but we have to run CFT analysis, as you see over here. This is our CFT analysis. And we also run, the experimental of the two different particles running in the market channel. Okay. So that you can take, if you're gonna be more interested on that, you can take a look at this, the published articles if you wish. Moreover, we have also studied two different cells in a Dean flow dominated curved channels. One of them is the MCF7. The diameter is around 20 micrometer. The other one is MBA 231. The diameter is 15 micrometer. As you remember that in the Dean flow and the inertial flow measurement, the diameter is going to be related to the power of diameter, power of the dimension. So it means that 15 micrometer and a 20 micrometer, if you take the power of 6 or power of 3, it's going to be a big difference in the force acting on the particles. In that case, maybe you cannot see clearly, but what we have proved that by changing the flow rate, in this case 2000 microliter per minute, almost there is no focus. But if you're going to increase that 2000, 3500 microliter per minute, you're going to get a very clear focusing over here. Okay. The other one is just, measurement for determining whether they are live or not, for coming from the biological measurements. This is the more important point over here. And what we have used one more time, MC7 and NDA, these are two breast cancer cell mixture, different parameters, and they are unlabeled, and we are successfully separated MCF7 cells from our design in the experiments. Not only that, recently we are working on this is ongoing process. Very interesting. There is a very interesting, the cells. We call it very small embryonic like stem cells. And in many cases, they are ignored. They don't, people, why do you do centrifusion in the blood analysis? So many times they are not taken into account, they are ignored. But unfortunately, they would have very important biological information. To get that biological information, we are studying on those cells with medicine school to come up with separating those V cell stem cells by means of the inertial approach. And the stem cells under work over here is around 3 to 6 micrometer. As I told you that this is ongoing, the research activity. Hopefully, we're gonna do it successfully and come up with very interesting research results. Moreover, we have also utilized inertial flows, inertial forces studying on the mechanobiology. What we have done by designing different microchannels, as you see over here, you see on the screen 5 different design of microchannels, and studying how if you're gonna let the cells flow through those channels by exposing them to the certain inertial or micro forces while they are flowing through channels, how the biological response of the cells are going to be changed or modified. Okay, very interesting results we have found that. One of the very interesting results is the following. We, let THP cells running through the channels for a long time, like half an hour, 1 hour, 3 hours, 5 hours, whatever. But on the other hand, we have also implanted HUVEC cells. They are not exposed to any stresses, but the THP cells, they are monocyte cells. They are exposed to the forces acting in the microchannel, in the microfluidic system. What happened is the following. When the monocytes are exposed to for over an extended period of time, the interaction between the THP cells and the HUVEC cell are considerably reduced. So as you see over here, the adhesion behavior, this is the control, this is the half an hour, this is the 3 hours. So it's a very clear dependence of adhesion by means of the mechanobiological forces created by the microfluidic systems. So it's actually we are trying to understand how the mechanical forces always we have in our body. We are trying to imitate that by using microfluidic inertial based microfluidic devices. Now we are working on another subject up until now, and normally cells, normally they are in micron size, but we have recently focused on the nano-sized particle separation. These are some of the snapshots taken from some published articles, very recent published articles. There are two approaches basically. The first one is that you are getting, you should get the effective length of the market channel for over a very long, so that the acting forces on the particles are going to be effective to manipulate the particles. But if the size of the particles are going to be smaller than the micron size, it's going to be like if it is around 500 nanometer or 100 nanometer, you're going to make this, the length of the microchannel could be very, very long, even maybe decimeter or a couple of tens of centimeters long. Practically, it's very, it's not reasonable. So that what people do, they, by designing a very interesting, the pump system, they're gonna make a kind of, let the pumping in a cyclic mode to this way or that way, so that by doing such a motion of the particles in a cyclic way, in a very short, in a normal length microfluidic channel, you can come up with the forces acting on the nano-sized particles would be very effective. Then you're going to manipulate the particles within such reasonable designs. Or you can play with the viscosity. By increasing the viscosity of the fluid, you can also manipulate the particles in the market channel as well. These are two approaches, but we are going to work with our design is going to be similar to that, but we are going to do some different design approaches. Hopefully we will get a good results, and later on we publish our findings. Finally, before going to conclude my talk, I would like to express one of the design of micropump we have accomplished, come up with the fabrication and the characterization at the end. And the reason I'm going to include that micropump design in this talk, we are using that micropumping in our inertial devices, inertial systems as well. What we have done is that nothing but just 3 bearing bars for just pushing the microfluidic, channel. The fluids are going to push by parasitic, the acting, so that you can come up with a very nice pumping action in the microfluidic channels. As you see, these are some of the design, previous design, the schematics. And here is the fabricated, by 3D printing design. But I should show you something over here. This is the micropump, the channel. While this bearing are pushing the fluids inside the micropump, the fluids going into the sunflower design and come up with the particle manipulation within this design. So that it is a kind of monolithic approach. The design and the pumping is going to be on the same plane. and you are going to fabricate that on the PDMS material. It's very cheap and one at a time use type of approach. You can employ that here as well. And here is the much more 3D visualization of what we have done. These are the latest version of Micropump design in our studies. And even here is one of the final version of the integrated Micropump. It is not much big. It is as small as a coffee cup, and you can carry that, and it is working with a very small battery as well. Recently, we have developed remote controlling of the pump. It is also manufactured, and also we apply for certain innovation competitions, and we got the first prize. Actually, we got the awarded in such competitions with my students. This is the final version of what we have got in the Micropump design. What is the result of how does it look like? I mean, depending on the RPM values, 5 to 35 per minute, round per minute, we can come up with the 2.5 up to 2.5 microliter per minute. It is very close to the quality of the commercially available and much expensive pumping systems, Schwinger pumps you can purchase. But what we have done, actually, we have developed our own pump and using that pump in our research studies as well. To conclude my talk today, I did a very brief introduction of what is what I mean by the microfluidics. What are the types of the microfluidic applications? Specifically, I have concentrated on the inertial microfluidic systems. Why? Because there is still very powerful. They are still very powerful platforms due to their ease of fabrication, versatility, and modularity. And moreover, the hybrid approaches could be possible, and it turns out to be recently very popular because when you can travel from idea to product realization, design of the channel in the inertial approach is very determining factor in performance and the efficiency of the inertial microfluidics. And also, many examples are available. You can still find very recent publications, even I don't know how many, a couple of tens of papers for each day on this inertial microfluidic approaches you can find in literature. And recently they are more inclined to the application parts of that technique. Multi-particle case is still to be challenged, and there is a room over here to be studied. And also, I believe that there is still plenty of room at the bottom in terms of design, modeling, and applications. Before concluding my last slide, I would like to thank you, my students, for realization of research, specifically on the inertial microfluidics. It's almost a decade-long list, actually. There are some current students as well, but there are some of them even already became faculty members at certain universities, but I want to keep their names over here because it's nothing but it's a research through collaboration. Thank you very much for listening to me. If you have any questions, happy to answer.
Yeah, anyone having any questions, you can please unmute yourself and ask the question, please.
Hello, this is Srini here from IRMAS.
Yes, sir. Yes, sir. Please post your question.
Chat. They're gonna post it on the chat.
Yeah. Okay. Actually, you have shown that photolithography, the process for manufacturing that micropumps. Can we try off silver screen printing process, printed electronics kind of stuff to manufacture that particular micropump?
Yes.
Instead of photolithography?
Yes, you can do that. The problem is the surface quality and that the dimension accuracy. As long as you're gonna satisfy that, you can. It is adaptable. You can do that. Okay.
Okay. Any other questions from anyone else? Yeah. Any other questions?
Questions may be written. May I do a stop share?
No problem, sir. No questions as of yeah.
I think there's one question. Maybe can we fabricate using printed electronics technique? To some extent, yes. The problem is design and how you can transfer your idea on the floor. Okay, I mean, but you know, you cannot achieve such design only using by printed electronics technique. You may utilize that, but it's not 100% satisfactory. Okay, I mean, you should somehow use a hybrid approach. Any other questions?
Thank you.
No problem.
Yeah, question from me. So apart from this biological applications, can you say any other engineering applications for that micropumps?
Yes, like one of the very recent and popular examples is that metallo-organic framework. Metallo-organic framework is the application from chemistry. People concentrating on how you can manufacture nano-sized particles or quantum dots even by using microfluidics. Why? Because you can very precisely control the concentration of the solvents by microfluidics. In a way that you can come up with a very interesting, chemically different, but with a minute amount, with different, you know, the nanoparticles. You can find such articles under the name of the metallo-organic framework by Microfluidics, MOF. It's very interesting. And another one, we are now working on that. We are trying to develop a system to measure that non-Newtonian, a rheology of the non-Newtonian fluids. We are going to achieve that by microfluidics. It is another very interesting example by means of the instrumentation of engineering.
Okay, thank you very much, sir. Any other questions, please? Okay, sir. I think no other questions. We have come. We can conclude this session.
Thank you very much. Have a good evening and see you soon face to face.
Yes, on behalf of organizing committee of IRMAS 2021, we like to thank you very much once again for allocating your time and sharing all these very interesting research areas regarding microfluidics and sharing your thoughts on it. We just appreciate that, and we like to thank you once again for that. Thank you very much.
Okay, bye now.
Okay, sir. Thank you very much.